Example 3.1, energy gain of a proton. A proton is placed between two parallel conducting plates in a vacuum. The difference in electric potential between the two plates is 450 volt. The proton is released from rest close to the positive plate. What is the kinetic energy of the proton when it reaches the negative plate? So in this picture, we have two charged plates, positively charged plate on the left and a negatively charged plate on the right. So initial case, this is the initial case. We have a positive, or yeah, we have a proton very close to the positive charge here. It's not moving. Initial velocity is 0. When you allow it to freely move, it would move towards the negatively charged plate because opposite charges attract, right? This plate is full of negative charges. This is a proton that has a positive charge, so it will move towards the negatively charged plate. Yeah, we need to find the kinetic energy of the proton when it reaches the negative plate. But what could be the initial kinetic energy? What could be the kinetic energy here? What could be the kinetic energy at this point? What could be the kinetic energy here? It will be 0 because kinetic energy, initial kinetic energy will be 0 because kinetic energy equals half mv square, right? So initial kinetic energy will be half times mass times initial velocity squared. Mass is a constant, cannot change. Only velocity can change. So initial kinetic energy equals half mvi square. Initially, the proton was not moving, so initial velocity is 0. So ki will be equal to half m times 0 square. So initial kinetic energy is 0. Okay. So we have initial kinetic energy. Our question is, what is the final kinetic energy? What is the final kinetic energy? Or we are going to find kf. Yes. One thing to note here is a positively charged proton is moving towards the negatively charged plate. So that's the natural movement of a proton, right? You don't need to do any work on the proton to move it towards the negatively charged plate. So the potential energy will decrease. If a positively charged particle is moving towards a negatively charged plate, then its potential energy U will decrease. If a negatively charged particle is moving towards a positively charged plate or something, again potential energy will decrease. And how can you increase the energy of the charge then? If you have a positive charge, try to move it towards a positively charged plate. That requires some work, right? Moving a positive charge towards a positively charged plate requires some work, right? And that work will be stored in this charge as its potential energy. So if you're moving a positively charged plate, positive charge towards a positively charged plate, you are increasing its potential energy. You can do the same thing with negative charge as well. If you have a negative charge, okay, blue color for negative charge, move it towards a negatively charged plate. You are increasing its potential, electric potential energy, right? Yeah. So negative charge moving towards a negatively charged plate, again potential energy will increase. Okay. In this case, potential energy is decreasing because we have a positively charged proton moving towards a negatively charged plate. Positively charged proton moving towards a negatively charged plate. That will decrease its potential energy. Now let's solve this problem. We need to find the final kinetic energy. So I'm going to start with energy conservation theorem. Energy conservation theorem. Conservation theorem for conservative forces. This is a conservative force, right? Yeah, so we can apply delta K plus delta U equals 0, or change in kinetic energy plus change in potential energy equals 0. But change in kinetic energy is final kinetic energy minus initial kinetic energy, and we have seen here, because the initial velocity is 0, the initial kinetic energy is also 0. Yeah. So if you substitute it here, it will be kf minus 0. So delta k will be equal to final kinetic energy. Okay, let's substitute back here in place of delta k. Kf plus delta u equals 0. I'm going to take this plus delta u to the right hand side. Kf equals minus delta u. All right, we are stuck now, right? We need delta U to find the final kinetic energy. Okay, but we have studied this equation. Potential at a point is the potential energy per unit charge. Potential energy for 1 coulomb charge, right? This is the equation for potential. To rewrite the equation for change in potential, you should consider change in potential energy per unit charge. Okay, that's our equation for change in potential. Yeah, okay, we need delta U, right? Sorry. We need delta U, and we have delta U here. So I'm going to solve for delta U, rearrange the equation to find delta U. It's Q delta V. Okay, I'm going to call this equation number 1. Let's call this equation number 1. Call this equation number 2. And I'm going to substitute equation number 2 in equation number 1. Okay, so I'm going to replace delta U with Q delta V. Kf equals minus Q delta V. Alright, so if you have the charge and the change in potential, substitute the values to find the final kinetic energy. We're talking about a proton. That's our charge in this problem. So Q equals, is it different? Yeah, Q of a proton is equal to 1.6 times 10 to the power minus 19 coulomb. That's the charge of a proton. What about delta V, change in potential? It's given that difference in electric potential between the two plates is 450 volt. Okay, so this is delta V. Delta V equals 450 volt, right? But you can see in this picture, the positive charge is moving towards the negatively charged plate, right? That would decrease its potential energy, right? That's the natural movement of the proton, right? Moving towards negative charge, right? So that will increases its kinetic energy and decreases its potential energy. Electric potential is related to electric potential energy. Delta U is decreasing, so delta U is negative, decreasing, so this is negative, so that will make delta V negative as well. Okay, so delta V is minus 450. In our problem, a proton that has positive charge is moving towards a negatively charged plate. That will decrease its potential energy. That's why we have negative sign here for the potential as well, because they are related. Okay, yeah, we are almost done. Now substitute all the values. Kf equals minus Q is 1.6 times 10 to the power minus 19 times minus 450. 7.2 times 10 to the power of minus 17. Unit will be joules because this is kinetic energy, right? Okay, it's a very small number because it's a proton. Yeah. Okay. I have an extra problem for you guys. This is our final answer. But what if they ask you to find the final velocity of this proton? How do you find final velocity? It's very simple. We have final kinetic energy, right? The equation for kinetic energy is half mv square. If we need to find final velocity or final kinetic energy, the equation will be half mvf square, final velocity squared. Solve for v from here. Cross multiply 2kf equals vf square. Mvf square. Vf square equals 2kf by m. Vf equals square root of 2kf by m. Final kinetic energy is 7.2 times 10 to the power minus 17. Mass is mass of the proton. Mass of a proton is 1.67 times 10 to the power minus 27 kilogram. The answer is 293,645.27 meter per second.